Welcome to the wonderful world of gases. Now, in order to understand gases, we're going to use something known as kinetic molecular theory, which has a couple of postulates that aren't perfect, but they work well enough and they allow us to understand gases and how they behave. So the first one of these postulates is that particles in a gas are in constant random motion. So these things are kind of just constantly bouncing around, and ricocheting off of each other. And postulate 2 says that there are no attractions or repulsions between particles. So when these particles do collide with each other, it's kind of like billiard balls. They just ricochet off of each other. They ricochet off the walls of the container and so forth. We're also going to say that the size of the particles is extremely tiny compared to the amount of space that's actually between them. So there's a lot of empty space in a gas, and this makes sense, right? Now, one other thing that may not seem intuitive is that by increasing the temperature, you're actually increasing the speed of the particles themselves. So it turns out the temperature is really just a measure of kinetic energy, or the energy of motion. So heating up a gas will actually just make the molecules move faster, and then cooling down a gas would make the molecules move more slowly. So you can imagine these things just kind of bouncing around, kind of like a ball pit at Chuck E. Cheese. The kids just kind of bouncing around all over the place. Or if you're a geek like me, a couple of years back, I actually got a really nice telescope in the mail in this massive package filled with packing peanuts. And so I just stuck my kids in there. And it's just like going to Chuck E. Cheese, right? They're bouncing around inside the packing peanuts. But these things are in constant random motion, just bouncing all over the place. Now, in order to understand gases, there are a couple of things that we need to understand, a couple of vocabulary words. And the first of these is pressure. Pressure is just it's force per unit area, right? So it turns out that if you have a gas in a closed container, and that gas is going to be exerting a pressure, a force upon that container. As the gas molecules kind of bounce around, they're going to be exerting, a force, right? So for instance, if I have, the sealed container here, and it's filled with a whole bunch of gas molecules, okay? So these things are all over inside of the bottle, right? And as these things move around, they're going to be colliding with each other and ricocheting off. They're going to collide with the walls of the container. And when they do that, they are going to exert a force, right, on that container. And we call this force the pressure. Now, there are a couple of factors that go into determining how high the pressure is going to be. One is the number of gas particles in a container, right? So by putting more particles in here, there are more particles that can now collide with the walls of the container, therefore pressure goes up, right? The other thing that we can do is alter the volume of the container. If I suddenly made this into a much smaller container, let's say that somehow we closed off this portion of the container and squeezed everything down. So now there's not nearly as much space in this container, which means all of those molecules or particles are now packed into a tighter space, which means that the pressure will go up, right? And then the other thing that affects pressure would be the speed of the particles. If they're moving fast, then that means that they are going to be exerting a greater force, right? So as these things bounce around faster and faster, you can imagine that it exerts a higher and higher pressure. And then remember, though, that the average speed of those particles is directly correlated to the temperature, right? So what we're really saying is that the temperature affects the pressure, right? You lower the temperature, the molecules slow down, they won't exert as much of a force. So how do we actually measure pressure, or air pressure? So air pressure is the pressure of the atmosphere pushing down on us. All of those gases, the nitrogen and the oxygen surrounding us, that's pushing down on us. Well, it turns out that you can use a barometer. Now, a barometer is actually just a simple little instrument, and fundamentally it's just a petri dish, right? And this petri dish is filled with liquid mercury, right? Liquid mercury is extremely dense, and so it's a very heavy metal here. And then you just have a little inverted tube with a vacuum in it. And it turns out that as the air pushes down on the mercury, it will actually force the mercury up into the this tube itself. And you can literally just measure how tall this column of mercury is, and that will be the air pressure. And so that leads to one of the units that I'll show you on the next slide, called millimeters mercury. Okay, it's literally how many millimeters tall the mercury column is. Now, the average air pressure or atmospheric pressure at sea level is about 14.7 psi, or pounds per square inch. That means that you have about 15 pounds of force pushing down on every square inch of your body all the time. Right? Well, why don't we notice it? Well, mostly because we're used to it, right? I mean, we don't, ever since the moment we were born, we've had 15 pounds of pressure on every square inch of our bodies, and it's only when that air pressure changes that we actually notice it. So, for instance, if you go to 10,000 feet up into the mountains, the air pressure there is only about 10 psi, which means that there's not as much atmosphere above you pushing down on you. And so this can actually cause your ears to pop as the pressure inside and outside of your eardrum starts to equalize, right? And if you can't get your ears to pop, we've all experienced that, where you start to build up that pressure inside of your ear, and it really starts to hurt. So what are the units for pressure? Well, there are a couple of them, and some are more common than others. The one that we'll most commonly use is the atmosphere, ATM. So it turns out that atmospheric pressure at sea level, the average atmospheric pressure at sea level, is exactly 1 atmosphere, 1 ATM. Now, I mentioned on the previous slide that millimeters mercury is also a common unit, and it turns out that 1 atmosphere is exactly equal to 760 millimeters mercury. So that's an important conversion factor, and one that you can use to go back and forth between atmospheres and millimeters of mercury. Torr is another unit. This happens to be the exact same thing as millimeters mercury, just named after Evangelista Torricelli, who invented the barometer. Pascals, kilopascals, not so common that we won't be using those commonly. And then psi, pounds per square inch. And this is what you use if you are inflating like a car tire or a basketball. Typically, it's rated in psi. Now, when we're working with gases, we're going to be using a couple of formulas known as gas laws. And there are a couple of variables that are vitally important in each of the gas laws. Now, not every gas law contains all of these variables, but every gas law contains at least some of them. So, the first one is P, which stands for pressure. Okay, we've already mentioned what that is. V is volume, the size of the container, the space that the gas actually occupies. T is temperature, and N is the number of moles of gas. All right. Now, one thing that I'm going to mention this several times throughout the lecture, is that when you are dealing with temperature, it absolutely must be in kelvins. All right. So no Celsius, no Fahrenheit. It has to be Kelvin, because Kelvin is an absolute temperature scale, which means you cannot have 0 Kelvin. You cannot have negative Kelvin. All right. Now, I'm going to mention a couple of the gas laws here, and you don't need to be concerned with these. Don't bother even writing these down or anything, because there's what's known as the combined gas law. It's going to combine, several of these together. And so that's the one that you should be worried about. But I'd like to go over each of these because I think that it helps us to understand what's really going on with the, with the gases themselves. So the first one is Boyles Law. Boyles Law says that for a fixed amount of gas at a constant temperature, the pressure and the volume of the gas are inversely related. Inversely related means that if one goes up, the other has to go down. Now this makes sense, right? Because if I have a balloon, right, with a certain volume, and I suddenly increase the pressure on it, right? I start squeezing on the balloon, what's going to happen to the volume or the size of the balloon? It gets smaller, right? Because the higher the pressure, the smaller the volume. And if I start to release the pressure, if I kind of ease off on it, then the volume's going to get bigger, right? The balloon starts to expand back out. So this is kind of the formula for the Boyles Law. P1 times V1 equals P2 times V2. Or in other words, the initial pressure times the initial volume is equal to the final pressure times the final volume, which means that if I give you any three out of those four variables, using a little simple algebra, you can actually solve for the remaining one. Now, it turns out that you use Boyles Law every moment of your life because you're breathing, and it turns out that Boyles Law explains how we're actually able to breathe. All right, you might think that when you're breathing, you're actually sucking in air, but it turns out that there's no such thing as sucking. All right, suckage is physically impossible. All right, nature does not suck, but it turns out that whenever you want to breathe in or inhale, your rib cage expands, your diaphragm lowers, and by doing that, you're increasing the volume. So by increasing the volume, you're decreasing the pressure in your lungs. So you now have a low pressure area in your lungs, and there's a much higher pressure outside in the atmosphere, which means that the atmosphere itself literally forces itself down your throat and into your lungs. And then when you want to exhale, your diaphragm contracts, your rib cage, contracts and closes in, and that decreases the volume in your lungs, which increases the pressure. Now you have a high pressure area inside your lungs, and that therefore it's higher than the outside atmospheric pressure, and it literally forces the air back out. All right, so Boyle's Law explains how you can breathe. Pretty interesting. The next law that we should be concerned with is Charles's Law. All right, Charles's Law says that if you have a fixed amount of gas at constant pressure, the volume and the temperature are directly proportional. Right? So that means that if one goes up, the other has to go up. Okay, so what does this actually mean? Well, this means that if I have a balloon, okay, let's say that you buy a balloon bouquet. All right. I personally hate balloons. I hate the smell of the latex. Oh, it's nasty. I think it's from working in the lab for so many years, having to deal with latex gloves, and just that smell gets ingrained in your hands. Oh, nasty. That's why whenever my kids get like balloons at the credit union or whatever, giving out free balloons, as soon as the kids are in bed, I go and I pop all those stupid things because they're so annoying, and then I blame it on the dog. So evil. Anyway, so you buy a balloon bouquet, and it's in the middle of winter. You walk outside into the cold, and what happens? Well, it's cold out there, and so therefore the balloons start to kind of shrivel up. And then you think, oh, these are faulty balloons. You walk back in. You're standing in line at the customer service counter, and as the balloons warm up in the nice warm store, suddenly they go back to their normal volume. And then you say, never mind. You walk back outside, and then the balloons shrivel up again. You run back inside and get in line at the customer service counter, and then they warm up and again until you finally realize, wait, Charles's Law says that when it's cold outside, it's lowering the temperature, which decreases the volume. They shrivel up. All right. If I increase the temperature, like I get into a car on a hot, sunny day, and if I leave the balloons in there, it turns out that they get so the volume continues to get bigger and bigger, and at some point the balloons can't stretch anymore and they pop because you've increased the temperature so much that you've increased the volume beyond the stretching point for the the latex itself. Okay, this is also explains why a hot air balloon works. Right, you decide to go on a nice romantic hot air balloon ride across the countryside, and as you're watching the sunset with that special someone, you should turn to them and say, this balloon ride is all thanks to Charles's Law, which says that if you increase the temperature of the this air by pulling this little handle here and heating the air inside the hot air balloon, that causes the balloon to expand, right? The volume to increase, which means that it's a lower density, and therefore the balloon rises up over this lovely countryside. I mean, that's just pure romance right there, right? Now, one thing I should mention, and I told you I'd mention this multiple times, it turns out that when we are dealing with the temperature here, the temperature absolutely must be in Kelvin, all right? Has to be in Kelvin. All right, one more law before we start talking about the combined gas law, and this is Gay-Lussac's law, which says that if you have a fixed amount of gas at a constant volume, that the pressure and temperature are directly proportional, right? Which means that if you increase the temperature, you increase the pressure. All right, or if you decrease the temperature, you decrease the pressure. If you've ever gone to like a, I don't know, like a scout camp or something, and you've been unfortunate enough to have somebody grab your asthma inhaler and throw it into the fire and it explodes, you know exactly what's happening with Gabeluss Law, right? So it turns out that inside that little canister, you're heating it up, right, by throwing it into the fire. It continues to get hotter and hotter. The pressure continues to get higher and higher, and at some point, the little canister ruptures. You can do the same thing with like a soda can. As long as you haven't opened it yet, like a closed soda, if you throw that in the fire, at some point it will explode. It's kind of dangerous, so you really shouldn't be doing this. But once again, when we are dealing with Gabeluss Law, we are dealing with temperature. Temperature absolutely must be in kelvins. All right. The other units, it turns out, for each of these laws, it doesn't matter what those units are as long as we're consistent. So if, pressure's in atmospheres, that's fine. If pressure's in millimeters mercury, that's fine, as long as it's always in millimeters mercury on both sides of that equal sign. So now let's actually get into the combined gas law. So this is an extremely useful law when we are dealing with initial conditions versus final conditions. Now, how does this work? Well, it turns out that if I give you some numbers, right? If I tell you the initial pressure and the initial volume and the initial temperature and then some of the final conditions, you can solve for the remaining one. So it's important to know the formula for this. P1 times V1 over T1 equals P2 times V2 over T2, right? So the initial pressure times the initial volume over temperature, is equal to the final pressure times the final volume over the final temperature. Now, let's go ahead and try working through a problem like this. So this is the type of problem that you can use the combined gas law for. So I'm going to go ahead and write the combined gas law up here. P1 times V1 over T1 equals P2 times V2 over T2. All right. Now, in this problem, it says a balloon contains 1.5 liters of nitrogen at 25 degrees Celsius. What will the volume be if the temperature increases to 55 degrees Celsius? So I'm given some initial conditions and some final conditions and then asked to solve for something. So when I do a problem like this, I personally like to write out each of my variables. P1, V1, T1, and then P2, V2, and T2. I find that by doing this, it allows me to just plug in what I know and then solve for what I don't know. So as I read through this again, it says that I have a balloon. It has 1.5 liters of nitrogen. Right, so that's my initial volume, 1.5 liters. And that gas is at 25 degrees Celsius. All right, and then it says, what will the volume be? So it's asking, what's my final volume, my V2? So I'm going to put a question mark there. If the temperature increases to 55 degrees Celsius, so my T2, my final temperature, is 55 degrees Celsius. Now, notice that in this problem, it does not mention pressure at all, which means that I can go ahead and just erase P1 and P2. I can also go ahead and erase P1 and P2 right out of my my combined gas law. So this is really nice, right? Because by removing that, I suddenly have one of those three gas laws that I mentioned earlier, right? All right, so suddenly this is Charles' law, and that's great, right? So by knowing this one combined gas law, I actually know all three of those other gas laws, and I don't even need to worry about those individually. Okay, so what's my next step? Well, my next step is to go ahead and double check my units. So notice that my volume is in liters. That's okay, it just means that my final volume also has to be in liters so that those will cancel out. All right, as long as my pressure is in the same units and my volume's in the same units, it doesn't matter what those units are. However, what about temperature? Well, temperature is the one that I absolutely must have these in Kelvin. Well, remember, to change something from Celsius to Kelvin, you just add 273 to it. So 25 plus 273 is 298 Kelvin. All right, and then my second temperature is 55 plus 273. All right, and that's 328. Oops. 328 Kelvin. So those have to be in Kelvin. Now I can go ahead and cross out the kelvins because those canceled. Now, all I have to do now is plug these into my equation. So I can do that now. I have my V1, which is 1.5. And I'm lazy. I'm just leaving off my units because I already canceled them out earlier, right? My T1 is 298. My V2, I don't know. I'm just going to call it V2. You can call it X, whatever. All right, so my V2, and then my T2 is 328. So now it's just simple algebra, right? I'm just solving for V2. So in order to do this, I'm just going to multiply both sides by 328. So that cancels out my 328, and therefore V2, my final volume, is equal to 328 times 1.5 divided by 298. All right, and this comes out to 1.7. All right, notice that in each of, here I had 2 sig figs. All right, here I have 3 sig figs and 3 sig figs. So I can only have 2 sig figs. So that's perfectly, valid to leave it as 1.7. And then what about my units? Well, I mentioned that these need to be in liters because my initial volume was in liters. If my initial volume was in milliliters, that's fine. It just means that my final volume would also be in milliliters. And so it turns out that if I increase the temperature, the volume is going to go up to 1.7 liters. Now I like to do a quick sanity check to see if this makes sense. So I have a balloon. It's at 1.5 liters. And it's at 25 degrees Celsius. I now increase the temperature. So what happens when I increase the temperature? Well, the balloon should start to expand, right? Because the balloon will get smaller if it's cold. It gets, larger if it's hot. And so by heating it up, it's going up to 1.7 liters. So sure enough, this does make sense. Let's go ahead and try another one of these. I'm going to go ahead and write out my combined gas law right up here at the top, just so I remember it. P1 V1 over T1 equals P2 V2 over T2. Now I'm writing out the full equation, right? And sometimes the problem won't mention pressure, or it will say it's at constant pressure, in which case I can go ahead and just erase pressure. If it doesn't mention volume, I can erase volume. If it doesn't mention temperature, I can erase temperature. But I like to write out the full thing, and then again, I like to actually write out each of my variables. P1, V1, T1, P2, V2, and T2. All right, so those are each of my variables. Now I can go ahead and read the problem. So it says that I have a balloon, contains oxygen. It's at a pressure of 712 millimeters mercury. So that's my initial pressure. It's starting out at 712 millimeters of mercury. And it has a temperature of 255 Kelvin. What will the new pressure be? Right, so what's my P2 if the temperature decreases down to 153 Kelvin? All right. Well, let's see. Does the problem mention volume at all? No, in fact it doesn't, which means it's my lucky day. I can go ahead and erase volume, or you could just cross it out, or whatever tickles your fancy here. And so I'm going to go ahead and erase volume right out of this. So that is gone. I don't have to worry about that at all. And now I go ahead and do a unit check. All right. My initial pressure is in millimeters mercury, which means that my final pressure has to be in millimeters mercury as well, because otherwise these wouldn't cancel. So I'm going to go ahead and cancel those out. My temperature is in Kelvin, which cancels out Kelvin. So that's kind of nice. I didn't even have to convert it to Kelvin. It was already there. So really all I need to do now is go ahead and plug these into my equation. So P1 is 712. T1 is 255. this is equal to P2. I'm just going to call it P2. And T2 is 153. Okay, so how do I solve for P2? Well, I simply multiply both sides by 153. Right, so this is just algebra. Since I'm dividing by 153 here, I'm multiplying both sides by the 153 to cancel that out. And therefore, P2 is going to be equal to, get out my trusty calculator, 153 times 712 divided by 255. And it looks like I have 3 sig figs in each of my original numbers here. So I can have 3 sig figs at the end of the day. So I'm going to call this 427. And what should my units be? They should be millimeters mercury, because that's what my pressure was in before. So that's my final answer. Now, again, I like to do a sanity check on a problem like this to make sure that it's actually making sense. And so I have this balloon. It's at a certain pressure and a certain temperature. Now I'm decreasing the temperature. So what should happen to it? Well, I remember that if I, increase the pressure, or if I increase the temperature inside of a balloon or an asthma inhaler or whatever, at some point it's going to increase the pressure so much it explodes. And so therefore, if I do the opposite, right, if I'm decreasing the temperature, then it should actually decrease the pressure as well. And sure enough, it goes from 712 down to 427. All right, let's go ahead and try another one. This one's from a true story, actually. I don't know about you, but when I was a kid, the big thing was to try to get pen pals, right? It was always, everyone wanted a pen pal, and one of the ways that you'd get a pen pal is you would actually take a balloon, you'd attach your little note to it that says, "Oh, please write back to Mike Cross at this address," and then you'd release the balloon, and it would fly up into the air, and then at some point it would land in like Africa or China or something, and some little kid would pick it up and say, "Oh, I want to be Mike's pen pal," and then they'd write to you, and you'd start this long-lasting friendship, and it would be wonderful. No one does that anymore, partially because we have email and Facebook and Twitter nowadays, and second because knowing my luck, I would probably release it, and it would fly like, I don't know, a couple miles and land in the state penitentiary, and some creepy guy would be like, "I'll be your pen pal, Mike Cross," and then it'd be awkward. So anyway, but it turns out that in 2001, there's a 10-year-old girl named Laura Buxton in England, and she did this, right? She sends this note up on a balloon, and it travels about 140 miles and lands next door, to another little girl named Laura Buxton, who is just shy of 10 years old, right? And so weird coincidence, like the Twilight Zone. And anyway, there's a fun Radiolab episode that you can listen to about this. But let's say that you are working with this, and you decide that while you're waiting for your pen pal to write back to you, that you're going to go ahead and do some gas law calculations. Lucky you, right? So let's go ahead and write our combined gas law here, and now I'm going to write out each of the initial units, or the initial variables, P1, V1, T1, P2, V2, and T2. And let's say that, I would give all of these numbers to you in a problem, but just to make some up, let's say that the pressure that day is about 1.01 atmospheres. The volume of your balloon is 950 milliliters, and the temperature that day is, I don't know, let's say 27 degrees Celsius outside. Now, you find out that once you release your balloon, it's going to go up into the upper atmosphere. You read in a book somewhere that, maybe the pressure there is only 0.70 atmospheres, way up there in the atmosphere. And it's cold up there as well, right? So maybe it's only 11 degrees Celsius. And you want to know, what's the volume of your balloon at those conditions, right? So while you're waiting for your pen pal to write back, you go ahead and crunch some numbers. So what we're going to do is we need to, in this case, use every single part of our combined gas law, right? Because it mentions pressure, volume, and temperature. Now let's go ahead and do a unit check. Notice that I have atmospheres and atmospheres, so that's good. I can cancel those out. I have milliliters for my volume. That's perfectly fine. It just means that my final answer also has to be in milliliters so that they cancel. What about Celsius? Is that okay? No. I need to change each of these into Kelvin, right? So 27 plus 273 is equal to 300 Kelvin, and 11 plus 273 is equal to 284 Kelvin, and that allows me to cancel out my kelvins, right? So now let's go ahead and just plug this whole thing into my equation. P1 is 1.01, V1 is 950. Oh, sorry, that's kind of a lousy 0 there. Alright, that's a little better. 300 is my T1. That's going to be equal to P2, which is 0.70, times V2, which I don't know, so I'm just going to go ahead and leave it as V2, over T2, which is 284. Now again, you can write in your units. I'm being lazy and leaving them off because I already canceled them out. Okay, now what do I do? Well, you can go ahead and use some algebra. I can multiply both sides by 284 and then divide both sides by 0.7, and that would solve for V2. I'm just going to go ahead and plug this whole thing into my calculator. So I'm typing in 1.01 times 950, dividing that whole thing by 300, and now I'm taking that answer and multiplying by 284, and then dividing that answer by 0.7, and this comes out to about 1297.6. But how many sig figs can I actually keep? Well, it looks like here I have 3, here I have 2, here I have 3, 3, and 2. So my quote-unquote worst number only has 2 sig figs, so I can really only keep 2 sig figs. So I'm actually going to go ahead and round that to 1300. My units have to be milliliters, and that's equal to my final volume. So my happy little pen pal balloon was at 950 milliliters. I released it up into the upper atmosphere. Now it's all the way up to 1300 milliliters, which explains why at some point the balloon's going to pop, right? And then it's probably going to fall into an ocean somewhere. A baby seal is going to choke to death on it. Some environmentalist is going to then, find this dead baby seal with the balloon and a note attached to it, and they're going to open it and find out it's me, and then they're going to blame me. And so I'm giving up with pen pals. All right, but this is our problem. So the next law that we should be aware of is what's known as Avogadros Law. And you've probably, hopefully, heard the term Avogadro or the name Avogadro before. This is the mole guy, right? So obviously this law involves number of moles. And it simply says that if the number of moles of gas in a container is increased, the volume of the container will increase as well. That kind of makes sense, right? If I have a balloon and it has 1 mole of gas in it, it's going to be a certain size. If I pump in another mole of gas, it's going to be twice as big. All right, it seems like common sense, but really the key point here that Avogadros Law makes is that the identity of the gas does not matter, which means that it could be carbon dioxide gas, it could be xenon, or it could be helium. It doesn't matter the identity of the gas. It'll always have the same volume, what we call the molar volume. But in order to work with this, we oftentimes will use standard conditions. All right, just kind of a set of conditions that everyone agrees on, so we can just say, oh, it's at standard conditions. We don't have to specify everything. So what are these standard conditions? Well, they're sometimes termed standard temperature and pressure, or STP, which is not Stone Temple Pilots, but STP, standard temperature and pressure. This is 1 atmosphere and 273 Kelvin. Or you can think of it as 1 atmosphere and 0 degrees Celsius, but you have to change it into Kelvin anyway, so 1 atmosphere and 273 Kelvin. And it turns out that there's a very important number right down here called the standard molar volume. And as the name implies, this is the volume of a mole of gas at standard conditions. And it turns out that the volume of 1 mole of any gas, and notice that this is underlined, that is important, that it could be chlorine, it could be sulfur hexafluoride, it could be any gas. If it's at STP, 1 mole will equal 22.4 liters, which means that we could actually use this in some really nice stoichiometry problems, right? Gas law stoichiometry, where we could use this conversion factor, that 1 mole of gas, of any gas at STP, is equal to 22.4 liters. All right, so kind of a useful number here. Now, this does lead to some kind of trick questions that I could throw at you, right? So let's say that I have these 3 balloons, okay? Let's say, yeah, you show up at a chemistry party and you have 1 balloon that's filled with helium, 1 that's filled with sulfur hexafluoride, and 1 that's filled with hydrogen cyanide gas. All right, each one contains exactly 1 mole of gas. They're all at STP because I make sure that all my chemistry parties are always held at standard temperature and pressure. So, which of these would actually have the largest volume? Well, it's a trick question, right? Because remember that these are all at STP, which means if these each contain 1 mole of gas, that 1 mole of gas will be at the standard molar volume, which is 22.4 liters. 22.4 liters, and 1 mole is at 22.4 liters. So, this is a trick question. They would all have the exact same volume. Now, the second trick question I could throw at you is, would they all have the same mass? No, right? They would all have very different masses, because if you look at your periodic table, helium, 1 mole of helium is about 4 grams, right? So this would only weigh approximately 4.0 grams per mole, right? Sulfur hexafluoride, this thing's massive. Let's see, sulfur is 32.06, plus we have 6 fluorines, and each of those fluorines is at 19 grams. So this thing's 146.06 grams per mole. Okay, that's a massive molecule. And then the last one would be hydrogen cyanide. And let's see, hydrogen's 1.01, carbon's 12.01, and nitrogen's 14.01. So this thing's about 27.03 grams per mole. So notice that the sulfur hexafluoride would have an extremely large mass, and the helium would have a very low mass. But they would all have the exact same volume as long as they're at the same conditions. Okay, so don't let me fool you with some of these trick questions. All right, volume would be the same. Mass would not be the same, though, because you have to look at the molar mass, which is you get from the periodic table by adding things up. Now, this would kind of be a fun chemistry party because someone would be able to, breathe in the helium gas and they'd sound like Mickey Mouse. And then someone else could breathe in the sulfur hexafluoride and they could sound like Darth Vader, right? Their voice would go really, really low. And then someone would breathe in the hydrogen cyanide and then they'd be dead. So actually wouldn't be much of a chemistry party. But the important rule here is make sure that if you do go to a chemistry party like this, make sure you pick first on the balloons, right? Or take a little sniff, and if it smells like almonds, don't breathe in that balloon. It's a really bad idea. Just pretend you're sick and go home early. Now, there is another law that we definitely need to know. This is a vitally important one. It's known as the ideal gas law. The ideal gas law just says that P times V equals N times R times T, right? PV equals nRT, affectionately referred to as pervnert. Okay, so P is pressure, we know that. V is volume. N is the number of moles of gas. T is the temperature. But what about R? Well, besides being a pirate's favorite gas constant, R, this is known as the universal gas constant. It kind of has a funny value. The one that we're going to be using is 0.0821, and the units are really weird. Liters times atmospheres over moles times Kelvin. All right, so 0.0821 liter atmosphere over mole Kelvin. I always think of it as latimolk because for some reason that kind of sticks in my brain, but it's important that we know these units, and the reason for this is that, remember when we were dealing with the combined gas law, I said that temperature has to be in Kelvin, but everything else, as long as the units are consistent with each other, you could use any units you want. So if your pressure is in millimeters mercury, that's fine as long as your other pressure is in millimeters mercury. If your volume's in milliliters, that's fine. Your other volume just has to be in milliliters. But when we are using the ideal gas law, we absolutely must make sure that each of our units matches up with the units in R. So our volume has to be in liters so that it will cancel out liters here. Pressure has to be in atmospheres, moles has to be in moles, Kelvin or temperature has to be in Kelvin, because that way everything will cancel. If something's not in those units, you must convert it to those units before you can actually plug it into the problem. So let's actually try this, see it in action. All right, so in this case, I'm going to be using PV equals nRT. Now, students always ask me, how in the world do I know which gas law to use? Well, it's actually pretty easy. The first thing is the combined gas law is the only gas law we have that has two pressures and two volumes and two temperatures. So if you're given a problem that involves two pressures or two volumes or two temperatures, you know that you have to use the combined gas law, because that's the one that has two of each, right? Now, the other thing is, this one, PV equals nRT, includes N, which is the number of moles. So if you're given a problem that involves moles, right, then you need to use PV equals nRT. Or if you're given a problem that actually involves grams, still the same thing, PV equals nRT, because remember that it's a simple process using molar mass to go from grams into moles. So let me go ahead and write out each of my variables. P, V, N, R, and T. All right, it says that I have a tank with a volume of 3.5 liters. So my volume is 3.5 liters. It contains 0.25 moles of gas, of nitrogen gas in this case. It's at a temperature of 22 degrees Celsius. I want to know what is the pressure. So question mark pressure. All right, notice that I'm missing R, but that's okay because that's a constant that I should remember. 0.0821 liter atmosphere over mole times Kelvin. Okay, so now that I have each of those, I'm going to go ahead and go in and double check that each of my units cancels. I have liters, which cancels out liters. I have moles, which cancels out moles. Ooh, I have Celsius. Celsius is not going to fly. I'm going to quickly add 273 to that to change that into Kelvin. So 295. Yeah, that's right, 295 Kelvin. All right, Kelvin cancels Kelvin. The only unit that I have left is atmospheres, which is perfect because my pressure is going to be in atmospheres so that it will cancel out. So just like before, I'm kind of going through making sure that each of my units cancel. If they don't, I make sure to convert them. So now that I have each of those, I'm going to go ahead and just plug them in to PV equals nRT. So P is my pressure. I don't know what that value is, so I'm just going to call it P. V is 3.5. This is equal to N, which is 0.25, times R, which is 0.0821. Again, notice I'm being lazy and leaving off my units because they cancel anyway. And then T is temperature, 295. So I've plugged in each of my values here. Now it's just a simple matter of solving for P, right? So to get P by itself, I'm going to divide both sides by 3.5, because that way it cancels out, and P is going to be equal to 0.25 times 0.0821 times 295 divided by 3.5. It looks like I have 2 sig figs to work with today, so I'm going to go ahead and round this to 1.7. And my units, notice, have to be atmospheres. So my pressure is 1.7 atmospheres. All right, excellent. So that is the ideal gas law at work. Not too bad, right? It's just a matter of making sure that my units cancel out and then plugging and chugging. Let's go ahead and try one more of these using that same formula. PV equals nRT. I'm going to go ahead and write out each of my variables, P, V, N, R, and T. All right, and I start to read through this problem. It says that I have a balloon. It contains 28 grams of CO2 gas. 28 grams. I don't have anything that I can fit grams into, so I'm going to keep going. It says that it's at STP. Oh, STP, standard temperature and pressure, right? So that means 1 atmosphere. So it's defined as 1.0 atmospheres for my pressure. What's my temperature? 273 Kelvin. Okay, I know the R is 0.0821 liter atmosphere over mole Kelvin. And let's see, it wants to know what is the volume. So question mark volume. I need N. N is the number of moles. Well, I don't have number of moles. Oh, but I do happen to have 28 grams of this stuff, right? Which means that I can go ahead and set up a problem, a quick domino problem, where I can convert my grams into moles. So that's just a matter of using the molar mass, right? So if I have 28 grams of CO2, oh, that looks really bad. Let me try that again. 28 grams of CO2. And I want to go ahead and convert that into moles, right? So question mark moles down here. I need the molar mass, which means that I need to add up the numbers from the periodic table. So I have carbon, which is 12.01, plus 2 oxygens, so 2 times 16, which comes out to a grand total of 44.01. So 44.01 grams is equal to 1 mole. Grams cancels grams, moles cancels moles. So let's see, 28 divided by 44.01. Looks like I have about 0.64 moles of carbon dioxide. So now I can go ahead and plug that in down here, 0.64 moles, and that's my N value. Now all I need to do is just double check that all my units cancel. Atmospheres cancels atmospheres, that's good. Moles cancels moles. Kelvin cancels Kelvin. So far so good. The only unit left is liters, which is good because my volume is going to be in liters, so that those can cancel each other out. What do I do now? Well, I just plug and chug. So P is pressure, that's equal to 1.0. V, I don't know, I'll just call it V. N is equal to 0.64. R is my same universal gas constant, 0.0821. And T is 273. So now it's just a matter of solving for V, right? I can divide both sides by 1, which I don't really need to because, just dividing by 1. But anyway, my volume here is going to be equal to 0.64 times 0.0821 times 273 divided by 1. I have 2 sig figs to work with today, so it comes out to 14. And what should my units be? They should be in liters, so therefore my final answer is 14 liters. So this really is a powerful formula. It allows us to, it allows us to figure out a missing variable as long as we know all of the other variables, right? As long as we know pressure, number of moles, the universal gas constant, and temperature, we can solve for volume, or we could solve for temperature, we could solve for pressure, we could solve for number of moles even. So a very nice formula allows us to kind of convert back and forth. So let me go ahead and show you kind of a fun example of being able to use a powerful tool to figure out something that's missing. All right, so as promised, here's a fun little thing that I can show you. I'm going to use this powerful little tool right here to be able to figure out what card you have. Okay, so it's kind of fun. I'm going to go ahead and just flip through the deck. You tell me when to stop. There. Okay, I'm going to go ahead and give you the top card. I'm not going to look at it. I'll just show it to you. So that's your card. All right, and I can go ahead and just put that back into the deck. Go ahead and just give that a quick shuffle just to make sure that it's nicely mixed in there. I'd let you shuffle it if you were here. And now I can go ahead and figure out exactly which card was yours. So your card was obviously the Jack of Clubs, right? Oh no? Okay. Well, since I couldn't figure it out, I'm going to go ahead and plug this into my handy dandy little card thing. You can see your Jack of Clubs right there, or my Jack of Clubs. And if you just focus, you can see that it actually changes into your card, which must have been the Ace of Spades. So this is the same type of thing as using the ideal gas law, right? You can't just typically look at a situation, figure out exactly what the missing variable is, but if you plug it into this powerful tool, then it allows you to easily convert everything into the correct missing variable there, like pressure, or volume, or temperature, and so forth. So the very last law that we should know about is known as Dalton's Law of partial pressures, and this is by far the most difficult and tricky of, no, actually it's not. This is actually the easiest of all of them. So it's very, very simple. All it says is that if you have a mixture of gases, you're not just dealing with a pure gas like oxygen. You're dealing with something like air that's a mixture of nitrogen and oxygen and carbon dioxide and radon and all that other good stuff in there. Well, it turns out that the total pressure of the gas is equal to the sum of what are known as the partial pressures of the component gases. So you're looking at the pressure due to the nitrogen, or in other words, the partial pressure of the nitrogen and the partial pressure of the oxygen. Just add those bad boys up and you have the total pressure. So, for instance, if I go ahead and give you a problem like this that says that you have nitrogen, oxygen, and carbon dioxide in this mix here, and I tell you the partial pressure of each. Nitrogen's 1.3, oxygen's 0.5, and carbon dioxide's 0.1 atmospheres, and I ask you for the total. That's pretty simple, right? All you have to do is add these up, and it comes out to 1.9 atmospheres. Not too bad, right? All right, so that's the total pressure, right? And that's Dalton's Law of partial pressures. Sometimes, if I'm feeling particularly evil, I might actually, not give you like one of these, right? I might just block that out. And then I would give you the partial pressure of the nitrogen, the pressure of the carbon dioxide, and then give you the total pressure. And then I'd expect you to somehow figure out the missing pressure. Mwahaha! It's actually not that hard, right? That just means I have to take 1.9, subtract 1.3, and subtract 0.1. And then it's pretty clear that the missing pressure must be equal to 0.5 atmospheres. All right, so please don't freak out if you see a problem like this. It's just the same old thing as usual, just a very slight twist on it. Now, the last thing that's just kind of interesting, doesn't really deal with calculations or anything, but partial pressures are important for our bodies because we're actually adapted to breathing a partial pressure of oxygen at 0.21 atmospheres. If you go climb up Mount Everest, the partial pressure of oxygen up there is far lower than here at sea level, and so we have a hard time breathing oxygen there. In fact, that's why I've heard that Everest is littered with old oxygen tanks, because people, as they're climbing, will just discard their used oxygen tanks off the side. The Himalayan people, the Sherpa, they're adapted to breathing partial pressures of oxygen at a much lower partial pressure, and so that's why they're able to, help climb up there without using all of these oxygen tanks and so forth. If the partial pressure of oxygen actually dips below about 0.1 atmosphere, it leads to what's known as hypoxia, and you die. But it turns out that you can even get too much of a good thing. If you're breathing in a partial pressure of oxygen above about 1.4 atmospheres, that leads to oxygen toxicity, and you die. In fact, you can even get too much nitrogen, and that leads to something known as nitrogen narcosis, and you die. This is sometimes known as the raptures of the deep, because if you're, going deep sea diving, and if you were to just use a tank of compressed air, the air, the pressure down there is so high that, you've basically increased the pressure so much that it leads to too high of partial pressures. So for instance, at a depth of only 30 meters underwater, the total pressure of air in your lungs, and that means the partial pressure of each of those gases in the air, is actually quadrupled. So if the normal partial pressure of oxygen in air is about 0.21 atmospheres, now you've just quadrupled that, right? And so now you're breathing in a partial pressure of about 0.84 atmospheres. All right, starting to get up, closer to kind of the danger zone. And so if you go below about 50 meters when you're diving, you're not supposed to use compressed air. You're actually supposed to use a mixture called heliox, which is helium and oxygen. This allows you to actually avoid breathing in too much nitrogen or too much oxygen and actually dying. So please be careful anytime you're doing this. Also, another interesting thing about when you're diving is when you are diving at a depth of, like 30 meters, notice that the pressure of those gases is quadrupled, right? And we've learned through these gas laws that you have these tiny little microscopic bubbles in your blood anytime you're breathing, inhaling, and exhaling, and so forth. And they have this very high pressure, right? At this point, it's quadrupled. So it's at about 4 atmospheres of pressure. And then, as you surface, the pressure pushing down on you from the water is much less. And so what's going to happen to those microscopic bubbles? Well, if you're decreasing the pressure, you're going to increase the volume. Those bubbles suddenly are no longer microscopic. They're much, much larger than they were. So if you surface too quickly, maybe the bubbles are now 4 times their microscopic size, and that can actually shred your internal organs. This is what's called the bends, which is why when you're deep sea diving, you should always give yourself enough time to very slowly surface, right? You move up a little bit, you inhale, exhale, allow those blood gases to kind of get back to this lower partial pressure, or this lower pressure overall. You surface a little more, and then again, inhale, exhale, and so forth. So a lot of really interesting things that come in handy if you ever decide to go deep sea diving. If you do, go ahead and invite me. Much appreciated. All right, thanks for exploring the wonderful world of gases with me.